right. This video is picking up on our sort of fourth installment of data manipulation, where the topics we're going to cover are joining two data sets with the tidyverse join functions and pivoting or reshaping data both from wide to long and long to wide. So let's get started. I have at the top of my script here, remembering to load in the tidyverse library if you have not already. And we'll be working with our surveys data that we have read in using our read_CSV function. And to get right into joining two or more data sets. All right, so this is a pretty common thing that you will want to do. It's often unlikely that all of your data will be in one CSV file. Instead, it might be in a different CSV file per year, or you may have supplementary data that you want to append to your existing data that exists elsewhere. And so it's pretty typical. And so it's great to really get in the vibe of these join functions because it'll make your life a lot easier. So in order to do this, we're actually going to read in a second CSV file that we have already stored in your data folder so that we can put the two of them together and demonstrate how this works. So to do that, we are going to create a new object called tail, and again, use the read_CSV function. And we are going to read in from our data folder, our tail_length CSV. And we can take a look at what this tail data is just by maybe calling the summary function on the tail data frame. And you'll see that it has two columns, record ID and tail length. So to supplement the data that we already have about our rodent surveys, we also have this one more measurement that was taken and stored separately, tail length, but it is stored alongside the record ID, which is really important that when you are joining data sets, you want to understand about what it is that the R and the computer is going to join on. So what is the thing in common? And so here we have a pretty straightforward case of having shared record IDs. You could take a look at that by also calling on summary of our surveys object and looking at the record IDs that we have. And it'd be good to compare, do we have all the same values, a minimum of 1 and a maximum of 3, 5, 5, 4, 8, same mean and median, which gives you a sense that these are likely all present in both data sets. And even if they weren't, these join functions are pretty powerful and there are ways to work around that, but that's always good to understand what is shared and not shared between these two data. So the logic of the join function, I'm just going to paste in here. This is similar to what you would find in a help file, but because there are many different types of joins, the help file actually looks a little bit intimidating. So for instance, I'm going to call up left join, and what you'll get in the mutate joins for dplyr help is a list of inner join, left join, right join, full join, and there are actually suites more of these kinds of joins. And so each one has a slightly different logic. And so we're going to talk about the basic logic and kind of let you play from there given what your data needs are. But so let's say we have a scenario where we want to take the tail data and join that to the surveys data. So we have just one more column. So we can call this surveys_joined. And what we're going to do is I typically use a left join, which the idea of left, I think, is sort of a, I don't know, kind of a weird naming convention. But what it means by left here is really just X. It's the first data argument that you're going to present R with, and the right is the second. So you can think of it as X or Y, first or second, left or right. And so what left join is saying is I'm going to start with the X or the first data set as sort of my base. And I'm going to look at the second one and join that to the first one. Take the right and join it to the left. So sometimes this just has to do with column order. Sometimes it has to do with priority of what data gets kept and what gets dropped. So for now, we're going to use our surveys as our left or X data argument. So X equals surveys, Y equals our tail data. And you'll see that if we actually just ran this without a by argument, the default of the join functions are to join by, and then it will go in and look at whatever column names are shared by the two data sets. And this can be really helpful, or it can be really horrendous, depending on how many column names you have in common and what it is you actually want to be joining by. So I would recommend generally specifying which column it is you want to join by. So we would do by equals record underscore ID. And so there are a lot of kind of trade-offs of letting that happen. For now, it doesn't make a difference, but it's good to know that this argument specification has a default and that you override it with that by argument. And this is really the basic premise of what joins are. Like I said, there's kind of a whole additional world of joins, and we can talk more about them in class, but this is the basic logic, and this will get you pretty far without having to dive into all the other nuance. And what I want to spend the rest of the video on is talking about pivoting or reshaping, because this, I think, takes a little longer to set in. And so if you had a chance to kind of listen to the spreadsheets video a few weeks back, and we hinted at it just briefly in class, is talking about this idea of tidy data and thinking about data structures and how important it is to understand the shape of your data. And what we meant by that with tidy data is that typically we shape our data as one observation represents one row. And so that's really great for analysis. It's a really great way of basically storing your data. But then there are times, whether that's wanting different kinds of data summaries, or it will become relevant when we start visualizing in the next couple of weeks about how you want your data to be shaped. And you may find yourself in a situation where you want to change the number of rows and columns based on the summaries that you're interested in. So I'm going to just plug these notes in here so that everyone can read them. And so let's say for our example today, we have a goal where we're going to create a summary table and reshape it in a few different ways. So let's say we wanted to look at the mean weights of each species in our surveys data, but by the number of plots. So that means we'd want a table where the genus name is on the left-hand side and the columns are different plot numbers with mean weights inside them. But so before we get too into that, we first can focus on just the first line of this goal, which is to compare the different mean weight of species between or by plots. So this calls on what we learned last week with the group by and the summarize function, where we're going to want to create a new object, maybe called surveys weight. And we'd start with our surveys data frame and pipe that. And just right off the bat, we know now by experience that there are lots of NAs in the weight column. So we're just going to filter those out to save ourselves some visualization headaches. And then because we want to look at the weight by each species genus, I guess I should be specific, each species genus and plot type, we're going to group by two different variables. So you can group by as many variables as you want. Here we want to group by two, which is genus, comma, and plot ID. So we can tell R to group by two different variables just by using that comma inside the group by function. And then we're going to pipe to summarize, and we want the mean weight. And we're going to give ourselves a new column name so that our resulting table is nice and pretty, and say mean weight equals mean, open parentheses, colon our weight column. And it's grouped alpha by genus. Great. Okay. So then we can take a look at our surveys weight output. And what we have is a table that is 196 rows long and 3 columns wide, where we have the idea of what we want to summarize, right? We have our genus and our plot ID and our mean weight. But if you were to put this, I don't know, want to read this in a paper or put it in supplemental material, you typically wouldn't insert something that is 196 by 3, right? Those dimensions just aren't very readable. They also don't really help us compare anything between plot IDs or by genus, for instance. So what we want to do is reshape this data to make it wider, right? And we actually want plot ID, each ID to be a column. And so we are going to talk through the logic of the pivot wider function here. And one thing before we do that is just like give us a sense of like what kind of shape we expect in this pivoted table. So reshaping to wider data. And a good way to kind of understand what you would expect your data to look like is to look at the unique lengths of the various columns that we're trying to reshape. So if we've used both of these functions in class before, but we're going to nest them in this way, where I want to look at the length. So use the length function of the unique values. So use the unique function of surveys weight $ genus. So this is just another way of telling us, right, that we have 10 unique genuses in our data, I don't know if that's the plural of genus. And we can also use this length unique nested function to look at the unique plot IDs. So how many plot IDs do we have? And we have 24 plot IDs. And so we want to make these the columns, and we want this number of rows. All right, and so the logic of pivot wider, if we'll open up the help file in a second. This is uglier than I want it to be. Okay, trying to make that more readable for you. But if you open up the pivot wider help file, a lot like the joins, there's a lot of arguments that can go inside of pivot wider. And some of them are not necessary and some of them can be really powerful, but we're just going to focus on what are sort of considered the core essential arguments of pivot wider today. And this is going to be the names underscore from and the values underscore from arguments. Where in pivot wider, you put your data, you then specify names from, which is the single column that has the thing you want to be your new column names. This always takes a second to sort of take in. But in our table, the column that represents the thing we want to be our column names here is plot ID, because we want 1, 2, 3, 4, 5, 6, 7, all through 24 to be our columns. And then the values from column is the column that has the values you want inside your table cells. So in this case, it's going to be mean weight. So we can go ahead and start specifying this wider table through our pivot wider argument, where we do pivot underscore wider. Our data, we're going to input it is our surveys weight summary table. On our names from argument, we just said this is the column that we want the names in that column to be pivoted wider to be our new column names. So that's our plot underscore ID. And our values underscore from, like I said, is going to equal mean weight. Okay, so we can take a look now at our weights wide and see if that is a lot more like what we wanted. And it is. So we now have a table that is 10 by 25, which does make sense. We said there are 24 plot IDs, and we also have a genus column, so that's 25. And we only have 10 rows, one for each genus that's represented. And in the cells, in this values from, we have our mean weight values. So now this is a much more readable summary table than the, whatever it was, 126 by 3 or 196 by 3. So this is taking data that is long and pivoting it to a wider format. But we can also do this in reverse. So the pivot longer function works quite similarly. Again, there's lots of functionality to it, but we are just going to talk about the core arguments of pivot longer, which are similar to what we saw in pivot wider with one extra, which is this columns argument. And so here we again input the data. We then have a columns argument, which are the columns you want to stack on top of one another. So here you can select many columns, right? And this is saying, I want to take all of these columns, across all of these columns, I want you to basically pivot them so that they are stacked on top of each other. The data will become that long. And then the names to argument is a new column name. So you'll have to specify this in quotation marks because it's a new column that doesn't yet exist, where you want to store the old, or what we'll call the wide column names. So right now our column names are 1, 2, 3, 4, 5, 6, 7 through 24. So where do you want those column names, 1 through 24? What column do you want them to live in? And then the values 2 is the new column name where you want to store the column values, so the mean weights. So in practice, the logic of pivoting and what goes in which argument, I think really takes some practicing. So definitely, hopefully we can let this sit in and play with it in class. But we are just going to pivot the data frame we just widened. We're going to now pivot back to the same size in theory that it was before. And so we can call a new object called surveys long, start our pivot longer function. Our data, we're going to now feed in our wide data. So we're going to take our weights underscore wide. And here, our column names is actually a bit tricky. Because like I said, we want columns 1 and then through 24. And we've learned that we can select columns numerically. So I might say I want the 1st through 24th column, or or we might say, oh, we want to call them by name. So I can actually go 1 through 24. But we're gonna come back to this. So this is going to be a bad example, but we'll specify our other arguments and play around with this columns argument a bit. But we know we want names 2 is going to equal, it's essentially whatever we want to call the names of these columns, what we want the column name of these current 1 through 24 column names to be. And so what existed before was that we called them plot ID because that's what our column names are representing. Our values underscore 2 is going to be the column name that's going to represent the values that are internal to this table. And so that's what was previously called mean weight. But what happens if we run this line where we specify 1 through 24 as our columns? R throws us an error because it says we can't combine genus and 1 because genus is a character and 1 is a double or an integer variable. And this is because when we call 1 through 24, here we are calling by location. So when you call something numerically, you're calling by location. And so what we really want to do is call these, we either want to call them by location properly, or we want to call them by name. So this is calling by location because it's a number, but it's starting with genus, right? Because genus is actually our 4th column. So if we wanted to call by location properly, we'd actually want to say 2 through 25, because in our weights wide table, our columns that we want to pivot actually start with column 2 and go all the way to 25. So this would work because this is, well, let's see, matched by multiple arguments. I didn't block out my calls equals 1 through 24. So this works, but I'm going to show you one more way to specify these columns. So calling by the correct location. But really, this is a lesson in just not to name your columns numbers because it can confuse R and it can confuse us as our users. Because we could also call it by name, but one way to bypass R's aversion to numbers as column names is that you can use the same button on your keyboard that is the tilde, that squiggly line, also has this backtick thing. And R will read 1 as a column name if you put it in backticks. So we'll go 1 through 24. Nope, that's 14. 1 through 24. So this is calling, did that wrong. And this is calling by name using backticks to bypass numbers as column names, which we shouldn't do. Right? Okay, so then we could blank that out, and this will also work in the exact same way, presumably, if I add. So sometimes when R gets really confused when it says error unexpected symbol, and then it just starts like reading your code back to you. That's a good error that is likely means you're missing a comma somewhere. So the unexpected symbol part is just like, I don't know what I'm reading because I haven't had my comma, which is really important for separating my arguments. So now this calling by name functioned the same as calling by the correct location, as opposed to this incorrect, but maybe easy mistake to make, which is calling by location, thinking we're calling by column number, but really calling by location. Anyways, what does our surveys long look like? In theory, it should look almost exactly like our initial summarized table looked like, which was called surveys weight. But they are slightly different, right? So this table is 196 by 3, and this table is 240 by 3. But this is because when we pivoted wide, we added a bunch of NAs into certain plot ID columns. And when we pivoted back long, it actually retained these NA values where there was no weight value for a given combination of plot ID and genus. Whereas when we summarized, because we had filtered those out, it immediately sort of just filtered out the NA weights. And so in some ways, this is good, this is bad. It really depends. It's just a feature of knowing your data and knowing what your output is telling you. But we have essentially gotten back to the original shape of the data that we wanted. And so I will leave you here with this, and we are going to practice this more in class.